Eukaryotic DNA replication, the elongation step. Now, when one looks at or compares the elongation of the prokaryotic system with the eukaryotic system, one observes that the molecular mechanistics is more or less conserved. The way the elongation or the way the DNA is extending in the lagging and the leading strand is more or less similar, with the difference mainly being in the molecules that are involved in the process and certain aspects that have to be covered, considering that the eukaryotic genomes are slightly more complex than the prokaryotic genomes. So let us look at the learning outcomes of this session. So once the replisome machinery is assembled at the replication forks near the origins, and the DNA polymerase alpha primase forms the primer template junctions on both the leading and the lagging strands, it is the DNA polymerase delta and the DNA polymerase epsilon that takes care of elongation of replication. Primarily, the DNA polymerase epsilon, along with the CMG complex, is involved in the leading strand synthesis, and the DNA polymerase delta, with different accessory proteins, synthesizes the DNA on the lagging strand. Now, the lagging strand synthesis is in fragments, as we know that elongation is always semi-discontinuous, with the lagging strand having what is called as Okazaki fragments, and the maturation of this Okazaki fragment is again a key focus of the elongation process. Another interesting aspect that is associated with DNA replication is that the newly synthesized DNA has to become or has to condense itself into at least a certain level of condensation. So primarily it goes to forming the chromatin. This is also carried out uh, in the elongation phase as the new nascent DNA is being formed. Now, let us look at or review the replication forks at the replication forks that are formed once the replication complex is assembled. So we all know that the two replisomes at the respective replication forks, when the DNA is unwinding at the replicator region, you would have primarily the CMG complex, which means that the CDC45, MCM2 to 7 complex, and the GINS, uh, forming what is called as a CMG active helicase. And this CMG active helicase in turn is associated with through the genes to what is called as the CTF4 subunit of the RPA that is able to associate with the DNA polymerase alpha. So as you can see, and both the replication forks, you have the CMG complex. This is essential, and all along through the entire elongation process, once the replisome complex has the CMG complex, the CMG complex is present all through the elongation process. So it is always part of the replisome at the replication fork. Now, the primer that is formed by the DNA polymerase alpha is extended by the DNA polymerase alpha itself because it has both the primase and the polymerase domains, and therefore the DNA polymerase alpha will extend the primer till about 20 nucleotides. Having done that, uh, it basically swings from the leading strand to the lagging strand and then carries out the formation of the primer and the extended DNA at on the lagging strand. Now, this switching from the leading strand to the swinging from the leading strand to the lagging strand is thanks to its association with the CTF4 complex. This subunit, the CTF4 basically is a subunit of the RPA, or it is basically something that associates with any protein that has a CIP box. So what is a CIP box? CIP box is nothing but a CTF4 interacting peptide. So as you can see, GINS has a CIP box, and hence it can interact with the CTF4. DNA2, TOF2, etc. They have CIP boxes, so they can interact with the CTF4. DNA polymerase alpha itself has a CIP box, and hence it can interact with the CTF4. So you may look at the CTF4 acting as a bridge or acting as a scaffold to bind to several different proteins associated in the process of replication. Here, what is interesting to note is this, that the DNA polymerase alpha, which has completed synthesizing the primer and the extended DNA, at the leading strand, can swing to the lagging strand. Or here what is basically observed is, here you already have the DNA polymerase alpha having synthesized the primer template junction, and now it has been swung to the lagging strand to synthesize the primer template junction. Now this is possible because of the genes binding to the CTF4. So the genes is part of CMG complex, but the CTF4 is able to maneuver the displacement of DNA pol alpha from one strand to the other strand, because this becomes the connecting link. So it can go from here to here, and you can see the CIP box is always connected to the CTF4. So this is something that is extremely important, and this allows the swinging of the DNA polymerase alpha from the leading strand to the lagging strand. And then what has been observed is that the DNA pol alpha is generally associated with the lagging strand itself. Now what happens is that once you have the DNA polymerase alpha forming the primer template junction, okay, and the pCNA is now loaded by the RFC. So once the pCNA gets loaded on the double-stranded DNA that is now formed thanks to the DNA pol alpha primase complex, this pCNA is now able to bind to DNA polymerase epsilon if it is the leading strand, and DNA polymerase delta if it is the lagging strand. So the switch from DNA polymerase alpha to the DNA polymerase epsilon, or the switch from DNA polymerase alpha to the DNA polymerase delta, is thanks to the pCNA. So the pCNA, which not only increases the processivity of the DNA polymerases, also is responsible for the switching, the DNA polymerase switching effect. So the DNA polymerase alpha, having completed its job, is now switched to DNA polymerase epsilon and delta, simply because they have a higher fidelity and higher processivity, so that the synthesis is more correct. Moreover, the DNA polymerase alpha has its 3' 5' exonuclease domain inactive, and therefore it cannot synthesize long stretches of DNA with high fidelity. It makes a lot of mistakes. About 10 raised to 10, 10 raised to 3 to 10 raised to 4 is the fidelity, while for DNA pol epsilon and delta, it goes as high as 10 raised to 5 to 10 raised to minus 5 to 10 raised to minus 6. Sorry, DNA polymerase alpha 10 raised to minus 3 to 10 raised to minus 4, and DNA pol epsilon and delta can go as high as 10 raised to minus 5 to 10 raised to minus 6. So definitely the fidelity and the processivity of DNA polymerase epsilon and delta is much greater, and hence there is a switch from DNA polymerase alpha to DNA polymerase epsilon and delta. So this is what is the review of what is present at the replication forks, and from this point on, it is basically elongation. So let us go to replication of the leading strand. So again, let us consider just one replication fork, and you can see that the CMG complex is associated. The epsilon, DNA polymerase epsilon, is already bound to the CMG complex because of one of its subunits associated with the GINs. So you have, as you can observe, the DNA polymerase alpha that is synthesized the primer, and it's a short RNA primer that the primase synthesizes, and then you have the DNA polymerase alpha synthesizing the DNA using the 3' OH of the primer that it has synthesized on its own. Now, therefore, as the replication fork moves over here, through a lot of studies, what has been observed is that the CMG complex is localized on the leading strand. So you can see this is the leading strand, the 3' 5' strand. So the CMG complex, the entire CMG complex, is actually localized on the leading strand. And this association with the leading strand has been observed to be quite tight. So this is something that has been observed through microscopic studies and also through single molecule studies. The DNA polymerase alpha switches to, of course, the lagging strand. So you can see that it has been removed. And due to the pCNA, now you have the DNA polymerase switch to DNA polymerase epsilon. So DNA polymerase epsilon, of course, has the polymerase activity. So it can synthesize from the 5' to 3' direction. And it has the same catalytic action as all polymerases. That is, through a nucleophilic attack using the 3' OH, it is able to add a nucleotide. Okay, so 3' 5' exonuclease activity is something that is present in the DNA polymerase epsilon, and hence, in lieu of the presence of 3' 5' exonuclease activity, DNA polymerase epsilon is able to carry out proofreading, making it a highly fiddle enzyme. So its fidelity is as high as 10 raised to minus 5 to 10 raised to minus 6. That is, a wrong nucleotide is added only per 10 raised to 5 to 10 raised to 6 nucleotides. It has, of course, a very high processivity on its own, and binding to the pCNA increases it further. So when one looks at the overall structure of DNA polymerase epsilon, it is found that it is again a multi-subunit complex, with Pol 2 being the largest subunit of the DNA polymerase epsilon, and the Pol 2 has the catalytic domain. This in turn is bound to the DPB2. This is significant as a subunit, and the DPB3 and the DPB4. Now, the DPB3 and the DPB4 are responsible for the enzyme's high processivity. So, the presence of these two, so what has been found is if these two subunits are removed from the DNA polymerase epsilon, then its processivity decreases to a great extent. So, these two have been attributed to giving high processivity to DNA polymerase epsilon. We of course know that DPB2 is responsible for binding to the CMG complex. So we know that once the replisome machinery is formed, the epsilon, DNA polymerase epsilon is already bound to the CMG complex in readiness to take over from the DNA polymerase alpha primase complex. But the only requirement is that the pCNA has to be loaded by the RFC. A small domain in the catalytic domain binds to the nascent double-stranded DNA. So you know that this double-stranded DNA has been formed by the DNA pol alpha, and the catalytic domain of the DNA polymerase alpha can bind to this double-stranded DNA and begin the process of synthesizing DNA. Now we look at the replication in the lagging strand, in the leading strand itself, to look at the same aspect as we mentioned, where it has been suggested that the entire CMG complex is localized on the leading strand. So several studies have actually shown that the MCM27, CDC45 and the GINS is preceding the DNA pol epsilon, and the entire complex, the pol epsilon, GINS, CDC45 and MCM27 is not bound to the lagging strand, it is only bound to the leading strand. The only connect that the CMG complex has with the lagging strand is through the CTF4. So, based on this interaction of the CMG complex with the leading strand, there are two models that have been proposed, by lieu of which the leading strand enters the single strand, that is, the leading strand enters the catalytic domain of the DNA pol epsilon. So, one of the models suggests that around 40 nucleotides of single-stranded DNA precedes the double-stranded DNA that the pCNA is bound to. So as the CMG complex keeps unwinding the DNA, there are approximately 40 nucleotides before the DNA that is associated with the pol epsilon, while there is another model that is suggesting, depending on the studies itself, that it is just about 20 nucleotides that precede. So you can see here there is slight looping out of the DNA, and that is why this takes care of the 40 nucleotide long DNA, whereas in this case, the entire single-stranded DNA that the CMG complex has opened up is present within the CMG complex itself. and it immediately enters the DNA pol epsilon. Now, while looking at various such structural aspects, they kind of suggestive, or there is a suggestion that these two models may be actually interconvertible. That means at times it has 40 nucleotides preceding the DNA pol epsilon, and at times it can just have about 20 nucleotides preceding the DNA pol epsilon. And as you can see over here, this is how the lagging strand is. So we now go to understanding the replication in the lagging strand. So replication at the lagging strand is an aspect that is dependent on the same thing, where you can see that the connection between the CMG complex and the lagging strand is through the CTF4. So the primase to polymerase shift evident in DNA pol alpha. You can see that from here, from when you have the DNA pol alpha binding to the lagging strand, it will first form a short primer. This zigzag structure is talking about this being the RNA part. So the primase of the DNA pol alpha synthesizes the RNA primer, and then there is observed to be a conformational change in the DNA pol alpha itself, by lieu of which you would have this primer, the 3' OH of this primer, used by DNA pol alpha itself to synthesize DNA. Now it is adding deoxyribonucleotides, and it synthesizes to up to 20 to up to 15 to 20 nucleotides. So that is how this portion is about 25 to 30 nucleotides long. The entire primer and the DNA, double-stranded nascent DNA that is formed by DNA pol alpha. Now, what is very interesting, therefore, to note is that the pol alpha, okay, has the primase domain, and the primase domain is able to synthesize only a very short RNA primer. That is thanks to there being a domain that does not allow the primase to synthesize beyond a point. Once the primer or the RNA is formed till it reaches that domain, immediately what happens is there's a conformational change in the DNA pol alpha, almost a turn kind of thing, and then it is the polymerase subunit that is now more close to the template. So it reads the template, and using the 3' OH of the primer that the primase domain had synthesized, it is now adding the next 20 nucleotides of DNA. Moreover, one point to be noted over here is that the DNA polymerase alpha is observed to bind with a greater affinity to the RNA DNA hybrid region, that is the primer template region, rather than to the nascent, that is the double-stranded DNA portion that it has synthesized. So therefore, because it binds with greater affinity to the RNA primer template, but with a lesser affinity to the DNA that it is forming, it is not, it is therefore not able to keep itself associated with the template for a long period of time. That is one observation. Second, when you have the double-stranded DNA formed over here, the pCNA is loaded by the RFC, and once the pCNA is loaded to the RFC, the synthesis by the DNA polymerase alpha is abrogated. So you only have a certain extent to which the DNA pol alpha synthesizes the primer template. Post which, once you have the pCNA bind to it, then the pCNA binds more strongly to the DNA pol delta, which is observed to be the polymerizing enzyme associated with the lagging strand. Although there are a lot of studies that show that DNA polymerase delta can also be associated with the leading strand synthesis in many organisms. But majorly what has been observed is that the DNA polymerase delta is associated with the lagging strand synthesis, and it takes over from the DNA polymerase alpha, uh, and the pCNA is increasing the processivity of the DNA polymerase delta to a great extent. So it does not have as much high processivity as the DNA polymerase epsilon, but When it binds to the pCNA, its processivity definitely increases. Secondly, because the DNA pol alpha from here has been removed, it is still associated with the CTF4. So as the DNA helicase is unwinding the DNA polymerase alpha will bind to a new region in the single-stranded DNA and start synthesizing the. So every few hundred base pairs of the single strand formed by the CMG helicase, you will find a primer being formed by the DNA polymerase alpha. The regions of single-stranded DNA are protected and stabilized by the RPA molecule, as you can see over here. Now, loading of the pCNA at the primer template junction is important, as mentioned earlier also, because it leads to what is called as a DNA polymerase switch. So in case of lagging strand, the DNA polymerase alpha is replaced by the DNA polymerase delta. One important fact to note about DNA polymerase delta is also the fact that it is able to carry out strand displacement, which the DNA polymerase epsilon, that is carrying out the leading strand synthesis, does not have. So DNA polymerase epsilon cannot displace strands, whereas DNA polymerase delta can displace strands. Now, how does this help in the lagging strand synthesis is what we will see in a short while. So now, therefore, what we have learned from here is that the lagging strand, through the similar trombone modal structure, is synthesizing the lagging strand in fragments. So every fragment that is formed should have a primer, and these fragments are discontinuous and they are the Okazaki fragments. So effectively now what should happen during elongation is that these fragments have to be made continuous. So how would they be made continuous? By, of course, removing the primer region, that is the RNA region, and by sealing so filling up the gap after removing the primer and sealing the DNA so that they become a continuous DNA. This is what is called as the Okazaki fragment maturation. So what we are now going to look at is how DNA polymerase delta is helping in the process of Okazaki fragment maturation along with other replicative accessory molecules. So let us consider that you have a primer template junction over here to which the pCNA was loaded, and from there on the DNA polymerase delta has started synthesizing the new DNA using the lagging strand template. The template it is begun to synthesize the lagging strand. It continues to synthesize and it is now approaching the next primer template junction on which you already have a nascent DNA formed. Now, when it reaches the primer of the previous Okazaki fragment, what is observed is that the DNA polymerase delta is able to displace the primer from the template. Okay. Now, this is something that the DNA polymerase delta is able to do. But what is interesting to note is with the strand displacement synthesis, one other characteristic of DNA pol alpha comes forth, and that is that due to its displacing the RNA primer, there is a slight change in its conformation, which leads to its 3' 5' exonuclease activity becoming dominant. And thereby what happens is when it adds one nucleotide, it tends to remove that nucleotide through the 3' 5' exonuclease activity. So although the flap is formed and the flap is the flap is definitely formed, so you have a 5' flap being formed. The strand displacement itself is counteracted by its 3' 5' exonuclease activity. All of you know that when it has to carry out the exonuclease activity, it takes a step back. So you can see that now what happens effectively is that it is neither going forward nor going back. It is staying at the same position. It is adding a deoxyribonucleotide and removing it, adding and removing it. So therefore, in a way, it is leading to a phenomenon which is called as idling. It is just lying there. What is the consequence of this idling? The consequence of this idling is that the flap size does not increase. So the flap is short. It is not a long flap. So this is something that has been suggestive of the fact that a DNA polymerase delta can go into idling to ensure that the flap that it has created is short. Now what happens to the flap? The flap is cut into fragments or into smaller fragments or into smaller nucleotides, one nucleotide each. Okay. And interestingly, that when the DNA polymerase delta, which has a good rate of catalysis, that is, it can add 20 to 50 nucleotides per second. Okay. Although what is observed is the rate is 50 nucleotides per second, but that is dependent on the level of DNTPs present in the cell. And however, on its own, if a lot of DNTPs are present, then it can go to the extent of adding 250 nucleotides per second. This speed at which it is carrying out replication is of course slowed down because of strand displacement. When it displaces one nucleotide from the template, it is slowing down. When it displaces another, it is slowing down further. So therefore, the entire polymerase becomes slow as it displaces and synthesizes. Therefore, again, this is ensuring that the flap formed is going to be small. Now, what cuts the flap? The cutting of the flap, many studies, of course, have revealed the use of FEN1, which is flap endonucleases. And what many studies have also suggested are that the eukaryotic system also has RNase H, and there are two RNase H, in fact, RNase H1 and RNase H2. RNase H1 has been observed to partake in the DNA replication in the mitochondria, but RNase H2 seems to have several substrates in vivo. They have been observed to help in repair. So, for example, if the DNA polymerase by mistake adds a ribonucleotide instead of a deoxyribonucleotide, then such ribonucleotides that have been added in the newly synthesized DNA are removed by RNase H2. What is also observed is RNase H2 can remove the primer region, the RNA region that is present in the primer template junction. So that also has been observed. While when the flap is being formed, then it is basically the FEN1, flap endonuclease 1, that cuts the. So it could either be FEN1 or it could be RNase H, although many studies have suggested that it is more of FEN1 that is involved in the Okazaki fragment maturation. Now, to continue to look at this, sometimes what can happen is that the DNA polymerase delta, instead of forming a very short flap, can result in forming a longer flap. This is also something that has been observed. Now, when a longer flap has been formed, especially in the yeast system, what has been found is there is another protein called DNA2, which is a 5' endonuclease. So, this DNA2 trims the flap. So see, again, what is resulting is a very short flap. Now, this short flap is removed by the FEN1, and the FEN1 is also recruited by the PCNA. The PCNA being a homotrimer, there are suggestions that this PCNA can follow what is called as a tool belt model. So the three monomers of the PCNA, one is bound to the DNA polymerase delta, one is bound to the FEN1, and the other one is bound to the DNA ligase. So when required, Pol delta is positioned to carry out synthesis. When required, the FEN1 is positioned to carry out the removal of the flap by its endonuclease activity. And then the DNA ligase, which is needed to seal the Okazaki fragments, is also associated. So once the FEN1 removes the flap, okay, it doesn't go away, it still binds to the PCNA, but here just for convenience I'm showing that the FEN1 has done its job of removing the flap. So what remains is a nick. Okay, so this nick has to be translated by so if there is a nick, so one or two nucleotides which has to be added is added by the DNA polymerase delta, and then you have the DNA ligase coming and binding and sealing the nick. So therefore, now what you have is a primer that was existing over here primer has been completely removed and now this has become continuous. The same will happen to this. You have a primer here, the DNA pol delta will displace this to form a flap and remove it. Okay, so that is how the Okazaki fragment maturation takes place. Now, there is another interesting aspect that we come into, and that is that DNA in the eukaryotes in the S phase tend to go back to the chromatin level immediately after the new DNA has been replicated. Now, here what you're seeing is initiation at the origins that are present in the DNA. This again is highly dependent on whether the pre-replication complex has been able to get access to the origin or the replicator. So because you have the DNA wound around the nucleosome twice, it is possible that the DNA that is wound around a nucleosome is not accessible. In such a scenario, it may be possible that if a replicator is present at the nucleosome region and the ORC does not get access, then that origin does not open at all. That is possible. So this thing of the fact that the DNA exists as a chromatin and that the origins have to be accessible has been taken care of the fact that the ORC complex and that to the ORC1 has a BAH domain that can directly bind to the histones of the nucleosome. And since it can interact with the chromatin, it is able to get in contact with the replicator region to lead to what is called as licensing of that origin and thereby eventually leading to opening of the DNA at the origin, which is called as the firing. So we have therefore the BH domains in the ORC itself responsible for marking the origins despite the DNA being in the chromatin form. That is thanks to the fact that ORC1 can bind to the chromatin. Now, once you have the origins opening, you know that one replication fork will move in this direction, the other replication fork is going to move in this direction, and that is thanks to the CMG helicases. So the CMG helicases are responsible for displacing the existing chromatin. So in this region, if there is any chromatin, then it is the CMG helicase that probably has to displace the existing chromatin. So as it opens up, it has to displace the existing chromatin. So how does it do it? There may be a molecular mechanistic which enables it to do it. So this is an extremely important fact. One another important fact about the CMG helicase at the origin is interesting to note. So there are several studies that have suggested that when the MCM27 was loaded by the CTD1 on binding to the CDC6 that is already bind to the ORC complex, it is attached in such a way that the two dimers of the MCM27 are attached to each other head to head. That is, the N-terminal domains of both the MCM27 are attached to each other, which means that you're basically looking at when you have the DNA unwinding, you should have the CTD region of the helicase facing the replication fork and the N-terminal domain behind the replication fork. But it is not the case. What is observed is that you basically have the CMG complex from here, okay, moving in such a way that eventually you will have the N-terminal domain towards the replication fork and the C-terminal domain being behind the replication fork, because this is important. Why is this important? But I hope you have understood the fact where originally it was the N-terminal domain here and the C-terminal domain here. The two helicases move, okay, in such a way that you have this fellow moving here and this helicase moving this side. So eventually the positioning of the two helices will be on the leading strand, but now there is a change. When it had bound with its NTD towards each other, but when it is going to open up the DNA, the NTD is opposite direction to each other. Why is this important? Because the N-terminal domain has been observed to be involved in the process of existing chromatin being displaced, okay, So there are certain molecules that can come and bind to the entity domain to initiate that. Moreover, the entity domain is required for binding to several other replicative accessory proteins. While the C-terminal domain has been observed to be more involved with binding to RPA, binding to the CTF4, binding to the genes, binding to, sorry, not genes, but CTF4, binding to the DNA pol alpha, etc. So, therefore, even the DNA polymerase epsilon and DNA polymerase delta. So, that is the reason why the C-terminal domain has to be behind the opening, okay, of the replication fork. So, this is something that is happening and it is very interesting. So what you observe at a replication fork is as the leading strand is synthesized and the lagging strand is being synthesized, the newly synthesized DNA you can see is already getting into the chromatin form. That means it is starting to get wound up on nucleosomes. So it again becomes what is called as a bead in the string structure with only a small part actually being not condensed. Now, here the observant thing that is there is that as the CMG helicase which is present over here moves forward, these existing nucleosomes are disrupted and they get into H3H4 dimer and H2A H2B dimer. So they get back into forming or get back into dissociated into the dimers. And it is these dimers that have been displaced that can be again associated with the newly synthesized DNA to form the nucleosome again, to form the chromatin again. So the observation is that new histones, so you can also have the de novo deposition. So you can have newly synthesized histone dimers that can deposit themselves onto the DNA to form the chromatin, or you can have the parental histones. So these are the parental histones. These can be deposited again on the newly synthesized DNA to form the chromatin. So both is actively happening. Please note over here that you can see that the post-transcriptional modification that is present on the histones, so lysines being methylated, lysines being acetylated, all that is already happening in the parental histones, but you can see that the newly synthesized histones also have such post-translational modifications. So a pool of parental histones dimers are formed due to dissociation as mentioned, and they can associate again with the newly synthesized DNA. Here what is interesting and what has been suggested is that we all know that histones being positively charged can bind to any part of the DNA because the DNA has a sugar phosphate backbone that is negatively charged. So the main attraction between the nucleosome and the DNA is because of its opposite charge. But there are lots of studies that have also reported that the deposition or the assembly of the nucleosome on a DNA can also be sequence specific. So they would prefer certain sequences over other sequences, and you can have a DNA winding around the histones or winding around the nucleosome thanks to a sequence that it has. So effectively what is being suggested is that the parental histones, okay, may again, it was disrupted from this point, say, now when the double nascent DNA has been formed, the parental dimer can associate itself again back to that same sequence. So that is something that is there. While the new DNA can, or the new histones can assemble on replicated DNA always behind the replication fork. So here that sequence specificity is decided by the newly synthesized histones, while the parental histones have their own sequence specificity that is possible. Now, so the question there arises is that are there molecular systems that help in the process of dissociation or disruption of the existing nucleosomes and the assembly of the new nucleosomes? Okay. So yes, there are several molecules that help in this process, and most of these molecules are chaperones and some are specifically histone chaperones. Okay. So, for example, what is observed is there is a molecule that is called as chromatin assembly factor 1. Chromatin assembly factor 1 are specifically able to bind to H3H4 dimers and bring them to the DNA and bind to specific regions on the DNA. So they are able to deposit H3H4 on the DNA to begin the assembly of the chromatin. Therefore, they are called as chromatin assembly factor 1. And assisting the CAF1 is another set of molecules which is called as anti-silencing function 1. Now this name has come because this molecule has been also observed uh, affect or to influence transcription by silencing gene expression, and therefore the name is there. But this also is helping the chromatin assembly by bringing the H2A H2B dimers. So it brings it to the CF1 where the CF1 is bound with the H3H4, and it gives it to CF1, and then the CF1 helps in assembling the H2A H2B on the existing H3H4 dimer which is already bound to the DNA. So thereby around a newly assembled nucleosome the DNA is bound again. So these two molecules help in assembly of the chromatin. Similarly, you have another molecule which is called as nucleosome assembly protein 1. This also is observed to bring in new H2A, H2B, and they are binding it to H3H4 that is already present associated with the DNA to complete forming the nucleosome. So this is again a nucleosome assembly protein. And you have another protein which is called as FACT. The fact are they are called so because they are facilitating chromatin transcription. So they have been found to have a role in transcription, again taking care of chromatin disruption and assembly. So this fact is able to bind to gins, as you can see. So it is bind to the CMG complex. ASF1 can also bind to the CMG complex, and fact is able to bring in again H2A H2B dimers to be deposited. Okay, so this also has a histone chaperone role where it is bringing an assembly, trying to assemble the dimers onto the existing H3H4 dimers, which is taken care of generally by the CF1. Thereby, NAP1, CF1, ASF1, and FACT are molecules that help in the chromatin formation on the new replicated DNA, and also the CMG itself, because of the N-terminal domain, is able to associate with other proteins that help in the disruption of the histones, existing nucleosomes. So together, so the understanding is there are probably several more chaperones that are involved in the process. So if you read more, you will get a lot of molecules associated with the replisome machinery to carry out this aspect of chromatin being associated with replication in the S phase of the cell cycle itself. So let us make the conclusions. Replication in the leading strand is by DNA polymerase epsilon. Here, because I forgot to mention to you earlier, DNA polymerase epsilon does not have the potential of strand displacement, and hence this is effectively carrying out more of the leading strand synthesis than the lagging strand synthesis, because for lagging strand synthesis a strand displacement is always a plus, or it is always something that is needed. But the DNA polymerase epsilon is known to have very high fidelity and high processivity, and of course a good rate of synthesis. So this also is able to add 250 nucleotides per second. The CMG helicase is known to be localized on the leading strand itself and guiding the polymerase to carry out the leading strand synthesis. The lagging strand synthesis is mainly by the DNA polymerase delta, which takes place, of course, in fragments, with the DNA polymerase alpha primase associated first with the CMG complex to synthesize the primer, and then the DNA polymerase delta takes over to initiate a replication. The pCNA, DNA polymerase delta, FEN1 DNA ligase together enable the process of Okazaki fragment maturation. Several chaperones aid in the replication-dependent chromatin assembly during elongation by recycling old histones as well as adding new histones. Thus, elongation of replication in eukaryotes in terms of mechanistics is very similar to that in prokaryotes as it follows the same trombone model. The only difference, like mentioned earlier, being the machinery having a lot of difference, especially with respect to the Okazaki fragment maturation and the chromatin assembly. Thank you.